Okay, so let's recap what I have done during the very end of the last lecture, because that was too quick. And I promise you that in the next lecture I will do all the necessary steps and apply to some example. Other than that, in today's lecture, basically today's lecture and the next lecture, it will be on the applications of what we have studied. Particularly, I have chosen certain examples which are useful in different subjects. For example, I'll talk about the integrals that involve sinusoidal functions, some function of sine theta and cosine theta. Because these kind of integrals, when you do electrodynamics or even in the gravitational potentials you calculate, you encounter the integrals which I'll write over here, these kind of integrals. And you know how to solve these integrals for the real variables, because then you have to do multiple expansion and you have to remember a lot of series stuff. And you will see that you will get rid of all this if you transform those integrals to the complex domain. So I'll solve this integral. And then we'll talk about some, because I have to talk about the Cauchy principal value. And today I'll talk a little bit about those integrals which later we will solve by the Cauchy principal values. Not in today's lecture, not in next lecture, but after that. In the second last lecture, I'll talk about the Cauchy principal value and the branch cuts and the other stuff, And if you remember, what we have studied is we have discussed the entire function, we have studied the simple pole, and we know that the Taylor sum is finite. There is no problem because it is a series that is written as a z to the power n, where n is positive number. And if I include the negative numbers also, then we have 1 over z plus 1 over z square up to so on and so forth. And I told you that the pole which is goes like 1 over z, or the linear power of complex variable at up singularity, that is known as a simple pole. And then there are the higher order poles. And we know that if we have a simple pole, the residue is the coefficient of that simple pole. And the last lecture we talked about how to solve the higher order poles and find the residue for that. And you remember I talked about this thing that suppose you have some function of z which you want to calculate at z is equal to z naught. And z naught is z minus z naught is a pole of a higher order. So we have highlighted the 3 steps. The first step was you have to multiply this function with this thing, first step. The second step was you have to take the derivative with respect to z of this k, where k is greater than or equal to n, you remember? And then you have to do this one, z minus z naught to the power k, f of k. And the third step was you can calculate the residue by setting this derivative, value of the derivative at z is equal to z naught. So the residue is c is basically 1 over k minus 1 factorial, whatever the power you have over here. And then you can write it as d k minus 1 over dz to the power d by dz k minus 1 z minus z naught to the power k and f of z at, I usually call it as z is equal to z naught. And I told you that f of z is an analytic function. So you can write, by the way, it is an analytic function, and you can have some higher order poles in that also, because then you have 1 over z square. Such a series is known as Laurent series. So you can expand this in the Laurent series I told you. Then you multiply this one with z to the power k, and then take a derivative. And do you want me to do all these steps? Because last time I have done very quickly. If you remember that f of z is, let me do it. F of z is summation n is equal to 0 to infinite a n z minus z naught to the power n. We usually call this as a regular part plus summation m is equal to 1 to infinite I wrote it as Cm z minus z naught to the power minus m. Now you have to do first step. You multiply this one with z minus z naught to the power k f of z. Then you can write summation n is equal to 0 to infinity an z minus z naught to the power k plus n plus summation m is equal to 1 to infinity Cm z minus z naught to the power k minus m. Now if you take derivative with respect to k minus 1, all k's will be gone, and you have to stop at n plus 2, because after that if you write the derivative it will be 0. So you can write this as d k minus 1 over dz k minus 1. Let me call this as, because I don't want to write it as f1 k, because that's too long expression and it's a waste of time to write it again and again. So you can do is summation n is equal to 0 to infinity an. Then you have to take a derivative. You write k plus n minus 1, k plus n minus 2 up to so on and so forth. Right? So you can write k plus n, and then you have n plus 2. And then you have what you will have over here. What is the power of z minus z naught? Any suggestion? 2 or what? N plus 1. Very good. Very good. Because a power less than this one. Plus, very good. Summation m is equal to 1 to infinity. And you can see that you have C1 k minus 1, right? Then you have k minus 2. But when you take a derivative of order k minus 1, k minus 2 becomes 0, because it has a power less than k minus 1. So you have summation m is equal to, let me write this one as plus. You can write this as plus C1 k minus 1 factorial. And you see this is the residue now. Now you have to do is the third step and take z is equal to z naught. This is a regular part and it remains regular when I took the derivative with respect to, when I took the derivative. Now if you put z is equal to z naught, so for z is equal to z naught, the answer is C1 is equal to 1 over k minus 1 factorial d k minus 1 over dz to the power k minus 1 z minus z naught to the power k f of z at z is equal to z naught. So all you have to do is, whenever you have the higher order pole, just follow these steps. And by following these steps, you can calculate the residue for that integral. So let's learn this with an example. Because when we apply this, then everything will become clear. So the whole idea is, if you multiply this with the k, where k is the order of the pole, the derivative will be 1 less than that. This is the punchline for this, to apply this one. So let me do this example. F of z is e to the power iota z over, let's say, z squared plus 1 whole squared. By the way, e to the power iota z is an entire function. Z squared plus 1 is an entire function, so there is no problem with the function. First of all, we have checked the properties of the f of z. Now you have to do is, you have to write this as z plus iota and z minus iota, and then you have square on both, because z square is z plus iota into z minus iota. And now you can see that you have a pole, higher order pole at z is equal to iota and z is equal to minus iota. So let me calculate. Let's take z is equal to iota. I can calculate for any one of the poles, and the other one is exactly the same. So what is the first step? Multiply by order of the pole. So you have to multiply, very good, z minus iota squared f of z, and this becomes e to the power iota z over z plus iota whole squared. What is the next step? You have to take a derivative with respect to z. It is 2, so imagine k is 2 and derivative is 1 less than that, so it is d by dz only, k minus 1, k minus become 1, and then you have z minus iota squared f of z. Now you have to take the derivative of this one. What will be the derivative? It's kind of a, okay, so this remains like this one, and this is e to the power iota z, and then iota, right, minus 2 z plus iota over z plus iota whole cube. Very good, thank you. ए की पार नहीं बढ़ती, 4 क्यों होगा? x का x स्क्वायर होता है, तो ये ऑलरेडी 1 है, तो कितनी 4 हो जाएंगी, 3 होंगी? 4 हो जाएंगी। ओके, चलो बस अब अपने कुछ भी नहीं करना, z को आयोटा पुट कर देना, एंड दैट्स ऑल, इट विल बी योर आंसर. So you see, now you have to put the pole over here, and it will give you the answer to that.
Minus e over power z plus iota minus 2. ये जो ऊपर शिफ्ट होगा प्रोडक्ट रूल लगाएगा.
अच्छा यार, मैं बेहतर अपने तरीके से कर लेता हूँ. Let me do it like this one. So it is d by dz of e to the power iota z, and 1 over z plus iota squared remains like this one, plus e to the power iota z d by dz z plus iota to the power minus 2. Now you can do it like this one. So you have iota e to the power iota z over z plus iota whole squared plus minus 2 e to the power iota z over. Now it's fine. Minus over here too. It's fine. Yeah. Now you can put z is equal to iota. Something, and you have to divide by 1 minus k minus 1 factorial, and that becomes 1 factorial, right? So now you have to do is 1 over 1 factorial, and then you take z is equal to iota in the last step over here. And this is nothing but this is iota squared is minus 1, and then you have e to the power minus 1, e to the power minus 1, 2 over. So you can do it. It's trivial now. So this you can apply to any integral that has higher order pole. First thing you have to check if your function is an entire function or not. And you will see, I'll apply this to cotangent pi z also. The cotangent and tangent, they have the problem because whenever the denominator goes to 0, because they are the oscillating function sine and cosine, and they pass by 0, so whenever they are 0, then we have a singularity. So I'll come to this point when I'll calculate the Riemann zeta function. Because you see, you remember someone asked that how 1 over n squared summation is pi over 6, and you will see with the help of complex variable we can easily prove that that is a zeta, the form of the zeta function, and zeta of 2 is equal to pi over 6. It is done in Rayleigh-Hobson also, so you can also find it over there. So this was the example related to last lecture. The goal of today's lecture is to solve the integrals of the following type. Suppose you have an integral go from 0 to 2 pi and you have some function of, let's say, sine theta or cosine theta and d theta. So how we can solve these kind of functions with the help of complex variables? I'll solve it with the help of a complex variables and then with the real variable calculus like multipole expansion stuff, and you will see that two answers will coincide. For one you have to remember a lot, for others you don't need to remember anything. But before that you remember the parametric equations. You remember I told you about the De Moivre's theorem that you can write z to the power n for any unit circle. You know the parametric equation for z is r e to the power iota theta, where r is the radius of a circle and theta is the angle on which you can move on the surface of the circle. So you can write this for a unit circle, r is 1. So this is parametric equation becomes z is equal to e to the power iota theta. So it means that you have z to the power n is e to the power iota n theta, and you know its expansion. You know that it is cosine n theta plus sine n theta. Similarly, you know sine is an odd function, cosine is an even function. Therefore, if you replace n with minus n, you have only minus sine over here. So you can also write z to the power minus n is equal to e to the power minus iota n theta, which is cosine n theta minus iota sine n theta. So this implies is if you add the two equations, you have z to the power n plus z to the power minus n over 2s cosine n theta. So you see, whenever you have these sine and cosine functions, you have written them in terms of the complex variable z. And once you have the z, you know the Taylor and Laurent series. So you can calculate the residues from that. And similarly, if you subtract the two, then you have z to the power n plus z to the power minus n over 2 iota is equal to sine n theta. So these two relations you have to remember, right? So whenever you see any integral that involves sine or cosine, replace this one if you want to solve it with the help of a complex variable. Minus. Thank you. Okay, so let me solve this integral. Let me take a very simple integral, and you encounter these kind of integrals a lot. Let's say I is integral 0 to 2 pi cosine 2 theta over a squared plus b squared plus 2ab cos theta. Do you remember where you have seen these kind of integrals? Let me write minus. Whenever you have a source at one point, you have to calculate the electric field or potential at the other point. You encounter these kind of integrals. And you remember this cosine, you apply the cosine identity of the cosine, and then you can write it like this one. So how to solve these integrals using the complex variable technique? My whole idea is b is greater than a and both are greater than 0. So it means that I'll confine myself, I will consider only those poles which comes inside. For example, suppose I have a pole of a over b and b over a. So I'll consider only the pole at a over b because b is bigger than a. So in 0 to 2 pi I have only those poles that do not involve b upstairs but b downstairs. So what is the first step? I told you how to do it. So okay, so you can say that, okay, I can write it as, first you have to calculate d theta also. So you can calculate dz is equal to e to the power iota theta, right? Iota d theta. So this implies is d theta is minus iota z to the power minus 1 and then you have dz. Now everything is written in term of z, and now you 0 to 2 pi becomes a full circle, therefore you have a closed contour. So this integrals become then integral over a closed contour, and then you can write cosine 2 theta as z squared plus 1 over z squared, right? You can write d theta as minus iota over z dz, and in the denominator you have a squared plus b squared minus 2ab, and instead of z, you cosine theta you can write set into 1 over.
Z power n plus
This is 2, this is 2, this is 1, this is 1. And now I have to write all the factors of half and the other. Now I have to write all those factors. You remember this has a factor of 1 over 2, and this has a factor of 1 over 2. I hope everything is fine now. If not, then let me know. कोई चीज कम तो नहीं लिखी? Okay, so you can just write it like this one now. So you have minus iota. Let me give it a simple shape, you know, minus iota over 4ab. You can check because there is no need to waste time on these simple things, and then you have a closed contour C. Then you have z to the power 4 plus 1 over z squared, and you have to multiply with this z to everything, and then you have a over b z plus b over a z minus x squared minus 1, right? You can take this to be common and then 2 and then cancel all the stuff. It's fine. Okay, so can you write it in terms of something that is, you see this structure a over b, b over a, and then you can see z square minus 1, and there is a do you think there is a simple pole at z squared? No, it is not a simple pole, but it is a pole of higher order. Very good. It is a pole of a second order. Very good. So you have to take care of everything, because if you consider it a simple pole, this is not a residue then. By the way, can you write this one as, if you take negative sign to be common, and then you can write it as, if you take the z sign inside, negative sign inside, then you can write it as iota over 4ab. Let me write it, and then closed, z to the power 4 plus 1 over z squared, z minus a over b into z minus b over a, and then dz. You can see, take minus sign, you have minus a over bz minus b over az plus and plus. Now you multiply them, z squared minus and minus becomes plus 1, and then you have minus b over az minus a over. It's perfect. Now you can see you have simple pole at z is equal to a over b. So you have double pole at z is equal to 0 and simple pole at z is equal to a over b. Why? Because b lies outside. So b over a is not a pole in any case, because b is bigger than a. And I'm enclosing it to a circle where a lies inside that one. Is okay? Now you have to tell me how I can calculate the residue. First of all, let me calculate the residue for z is equal to 0. What we have to do is we have to calculate the residue for this pole, we have to calculate the residue for this pole and add the two. So how to calculate the residue? Okay, let me calculate first the residue at, A over B. All we have to do is, we have to multiply both sides with this one so that it is gone, and then we have to put Z is equal to A over B. So then I have, this is my function of Z, now this is a function of Z. Instead of a theta, this is a function of Z, so you can write Z minus A over B, f of Z, and then take Z is equal to A over B. So you have to put A over B, Z is equal to A over B everywhere except at where Z, except in Z minus A over B. So you have iota over 4AB, and then you have A to the power 4 over B to the power 4 plus 1 divided by A square over B squared, and then you have A over B minus B over A. It's fine? Can you simplify this one? I can write the answer of this one, yeah. Because the simple means, and then you have, this is equal to, you can verify that this is equal to, and you remember one thing also, 1 over 2 pi iota stuff also, remember? Because when you calculate, okay, I'll multiply this 1 over 2 iota at the end, so there is no problem. I have just calculated the residue. This residue part of a contour of 1 over 2 pi iota, I will multiply it at the end. So you have, this is equal to, so just forget about this factor right now and calculate only this one. And then you have this equal to minus A to the power 4 plus B to the power 4 over AB into B squared minus A squared. It's very trivial, you know, B squared, A squared. I took a negative sign and then become A4, B4. 3 B's will cancel, 1 A is left, so fine. So this is the residue of this function, except this factor, this one. This I'll take care at the end. How about Z squared then? Now I have to calculate residue at Z is equal to 0. How to calculate this residue? Multiply this with Z squared, take a derivative, and then put Z is equal to 0. And you can verify that the residue at this one is equal to A over B plus B over A. By the way, it's not difficult. This one, all you have to do is you have to differentiate that. So this is now A squared plus B squared over AB. You can just multiply that and you will see. That's why I said. You will see that you have a factor, because you can take 2AB outside and then you have to write 2AB and you have 1 over 2 from there and you will just write it. You can just do it and you'll see. Okay, so what I have to do is I have to take a residue now. You see, I'm not worried about this factor much. I'm worried about only this function, right? So you can see that what you have now, you have to add the two poles. My residue becomes my full residue for this becomes, you have to add this one residue with the sign, you have to add this residue with its sign, and then you have to divide by 1 over 2 pi iota. 1 over 2 pi iota comes because you are closing the contour on the which side? On counterclockwise side. Okay, so then you have, the answer is, my total residue is 1 over 2 pi iota over 4AB, and then you have to, all you have to do is you have to put this one, A squared plus B squared over AB minus A to the power 4 plus B to the power 4 over AB into B squared minus A squared. So everything is gone, that is gone. So now you can do it like, you have to simplify this one. You have B, this becomes A4 minus B4, this is minus A4 minus B4, so A is gone. And you can just simplify this one and verify that the answer is. I'm not wasting much of my time on that one because all we have to do is we have to just simplify that, nothing else. So you can find the answer, right? And the answer is pi A squared over B squared into B squared minus A squared. Okay, so this is the answer with the help of the residue theorem. So okay, you can check this one. Excuse me. If there is a 2ab, there is no problem. Then you have 2 over here, right? Instead of 4. Okay, so sure. You can check it and then we can correct that. No problem. So the whole idea is you have this factor. That is more important along with this part. Now you do it with the real variable calculus. Go home, expand the series of 1 a square plus b square minus 2ab cosine theta, expand the Fourier series, add the identities of sine and cosine and prove that the answer is this one. This is a small assignment, very small assignment. All you have to do is you have to use two identities, that 0 to 2 pi cosine n theta cosine m theta is equal to pi times delta m, and this is the one identity that you have to use. Because if n and m becomes one with the same, then you have cosine squared, and you can always write cosine squared as a, you can always use that formula 1 plus sine or 1 minus sine in double angle form. So this you can easily do it one. And the other one is you have to expand this series 1 plus r minus 2r cosine theta. You can write it as 1 plus 2 times summation n is equal to 1 to infinite r to the power n cosine n theta. Upstairs you have cosine 2 theta, so it means n should be equal to 2, and you can verify that the answer will be the same. Right? So you see, someone has to tell you these identities if you don't remember them. But for the complex variable, you need not to memorize any identity. You just have to do a very simple calculation, which you have done with with the very basic concepts of the residue theorem that you have. So that is the part of residue calculus. You can always solve these kind of integrals. And these kind of integrals, I'll tell you, let me state one lemma. I'm not going to prove that because that is unnecessary to prove. I'll tell you how to use that. And you see that all these poles are on the real axis. What happens if we have the pole on the imaginary axis? I mean, all these poles are along real of z. If I have some poles on the imaginary axis, how to solve these poles? And there is a very famous Jordan's lemma for that. And there are 3 conditions of that lemma. I'll state those conditions, and then through examples, 1 or 2 examples, I'll demonstrate that. So good thing is, go home, read the chapter 6 of Marion and Thornton. He has written these kind of integrals in the gravitations chapter, as well as in the 3rd chapter of the Griffith and electrodynamics. You can see a lot of these integrals in the multipole expansion. So try to solve these integrals with the help of these residue theorem and match your answer with the one given in the book. I guess the French name, so it's Jordan lemma, so whatever you say now. For us, it's a Jordan's lemma. So you have to check 3 conditions before you apply this lemma to calculate the contour, to calculate the integral of any function. The first one is, do you want me to write that, or I can just state that. Suppose you have a function f of z that is analytic everywhere except in this circle of radius r, else it is analytic everywhere. It has a pole on the imaginary axis, right? It can have poles over here, here, anywhere, not on the real axis. This is one condition. The second condition is you have to take a semicircle of radius capital R, and this R is bigger than R naught. And what will happen if you take R to be infinity? It means that you have to calculate the maximum value of the integral, and if you take R to be infinite, upper limit on this integral, if you take R to be infinity in that limit, the result should be equal to 0. So these are the three steps. First, your function is analytic outside this one. There are few poles on the imaginary axis because this is real axis. This is my real of z. I always write it from now on as x, and this is my y, which is imaginary of z. And then what I do is I calculate the maxima of integral and then take r is equal to r to infinity and see if that is equal to 0. So once it is done, whenever I have these kind of integral, I'll write their answer to be equal to 0. And I'll apply it to two examples today. So if these conditions are satisfied, then this one is the final. That suppose you have any semicircle CR in the limit r goes to infinity, e to the power iota az for a to be positive, f of z dz is equal to 0. This was the you have mr, third condition, and then take r to be infinite, and then this integral will be equal to 0. And I have to prove this one. This one is the Jordan's lemma, three conditions. Let me do it for simplest integral. Let's calculate this integral. CR on a semicircle of radius r, e to the power iota z over z squared plus a squared dz. This kind of integral will come many times. For example, even in the, if you take z is equal to 0, and instead of this you take a summation 1 over n square, you can easily get from these integrals also. So it means that z square plus a square in the denominator, we have to solve this integral at least once. And you will see that a lot of applications of these integrals in next few lectures. So can you tell me that first two conditions are satisfied or not? F of z is definitely an analytic beyond some range, definitely. It has a pole on z square is equal to minus a squared. This implies z is equal to plus minus iota a. So you can see that the poles are on the imaginary axis. And I will consider only those poles in this semicircle for which imaginary of z is greater than 0, because it's a semicircle. If I have to take this one, I have to enclose the semicircle downstairs. So I'm considering only the pole for which imaginary of z is greater than 0. So the two conditions are satisfied. What I have to do now is I have to find the maximum value of this integral and then put r is equal to and then take r, limit r goes to infinity. So can you help me how to calculate that? We have to calculate the modulus, right? So that e to the power iota z over z squared plus a squared. So it is equal to e to the power iota z over z squared plus a squared, because mathematically there is no problem with it. What is z? Remember what is z? So it means if you have iota cosine theta, and whenever you have anything oscillating, take its mod, answer becomes 1. And then you have this one is equal to e to the power minus r sine theta. Is it correct? It's correct, right? Because you put r cosine theta plus iota r sine theta. You take r cosine theta, the absolute becomes 1 because it has iota with it, and this becomes minus r sine theta. What will be the in the denominator? No, tell me exactly. How to calculate the modulus of this one? No. You remember, z is not this simple one. It's cos theta plus iota sin theta. You have to take a square of it. How you can calculate the modulus of a complex number? Z squared plus a squared, z squared plus a squared. You can take a star and this becomes z squared plus a squared modulus square. And there is no problem with this star because this becomes z star squared, and you remember cosine theta, sin theta identities. And then you can do is, you can write z squared plus a squared, this becomes square root of r to the power 4 plus a to the power 4, then what? Of course, there is a z squared, so you have cos 2 theta plus iota sin 2 theta. This one, square root. Then your function become, you have e to the power iota z modulus over z squared plus a squared modulus is e to the power minus r sin theta over r to the power 4 plus a to the power 4 plus 2a squared r squared cosine 2 theta and then square root. You remember you have to find the maximum value of this r at this one. When this function will become maximum? Sorry. When numerator becomes maximum, denominator become minimum. So it means that if e to the power minus r sin theta, this goes to, let's say, 1 maximum, and you can say that cosine 2 theta becomes minus 1, so that you have a negative sign over here and then you have the minimum value. So you can, other condition is cosine 2 theta goes to minus 1. Right? Exactly. So then you have r4 plus a4 minus 2a squared r squared square root. What is this? What is this then?
R square minus a square
Whole square, exactly. Then this becomes r squared minus a squared whole squared. Exactly, without square root. And you have e to the power minus r sin theta goes to 1. What is the maximum value of this integral then? What is maximum value for r? 1 over r squared minus a squared. So any function that you are given, take its modulus, right, and see its behavior at r goes to infinity. If it goes to 0 at r goes to infinity, then according to Jordan's lemma, its integral on that contour is always equal to 0. So this goes as then, so then e to the power iota z over z squared plus a squared modulus. They usually define it as some maximum value for r is equal to 1 over r squared minus a squared. And remember, a is positive, a is greater than 0. So you can see that if you take limit r goes to r goes to infinity, m of r becomes 0. So these are the three steps. First step, you have to check the poles, then you have to write a semicircle, and then you have to calculate the maximum value of the integral, and then take r to be infinity, and the answer will become 0. Let's apply this thing. Any question if you have, by the way. It's clear?
Yes.
So if you have any question, I can just give a pause over here and you can ask. ये function है पूरा. This is whole function. Our function was e to the. You remember I said e to the power. I wrote e to the power iota az f of z integrated upon instead of a you have 1, right, in this one. F of z is 1 over z square instead of a, let me write it. It's b. So your b is 1, f of z is 1 over z squared plus a squared. It's perfectly fine. That's why I said that this whole function, this has to, the maximum of this should go to 0 when I take r to infinity. Let me apply it to one example and then everything will become clear. This was an example, but let's do it. Let's do an integral which is not that trivial to calculate otherwise, and then we apply Jordan's lemma and then see how it works. So this is very useful to calculate the Fourier integrals. When you have f of z sine az, f of z cosine az, these kind of integrals from minus infinite to infinite can be calculated with this one. So this I forget to mention that if you have these kind of integrals, and there are let's give it as an intuitive guess what is happening. Suppose you calculate these integrals from minus r to r and then take r to infinite. Instead of an exponential function, you have sine. So real part of an exponential function is cosine and imaginary part is a sine. It means the integral that you have mentioned, right, that you have done in the calculation, if you solve that integral, then perhaps you can solve these kind of integrals easily, and I'll find the answer of these kind of integrals and see limits are minus infinite to infinite. Yes, please. G, Jordan's lemma में imaginary. Let me do it like this one. उसी की application है. So these are Fourier integrals, you encounter these kind of integrals. Just look at the limit minus infinite to infinite. What I'll do is I'll shrink the contour first. Take it from minus r to r and then see if r goes to infinity. And then it becomes minus infinite to infinite. So let's do one integral, and from that integral we will infer the answer of these kind of integrals. Any other question, please? On one side we'll take minus r because in any case it's a limit, One quarter is on this side, other quarter is on that side. Okay, so if you have e to the power iota pi r, you can go on that axis, minus r axis. So r is positive still, but the value of z, which is equal to minus r, is negative now. So there is no problem at all. Once you take a in between the diameter, it's 2r. Let me solve this integral, which I have done right now to demonstrate the Jordan's lemma. Let me solve that integral in the limit from minus infinite to infinite and see what will be the answer. So suppose you want to calculate this integral, any closed contour e to the power iota z dz over z squared plus a squared. This is a closed contour, right? Can you do it like this one? So this is equal to minus r to r e to the power iota z over z squared plus a squared plus a contour on a semicircle e to the power iota z over, or not. You can always do it, right? Because you can always define like this one. You can go minus r to r, right? You can go like this and then go like this one. There is no problem. It becomes a closed contour then. Because there is no pole over here, You can see z square plus a square as you asked. Pole is not on a real axis, pole is on an imaginary axis. So there is no problem, you can go on minus r to r without encountering any pole. I will demonstrate what will happen if we have a pole on the real axis also in the next example. And then this will be a complete chart to solve any integrals that you encounter in the Fourier series. Whether you have a pole on the real axis, whether you have a pole on imaginary axis, imaginary of z greater than 0, imaginary of z less than 0, the technique will be the same. And if you take r to be infinity, then what will happen? In the limit r goes to r, limit r tends to infinity, then you have minus infinity to infinity e to the power iota z over z squared plus a squared dz. And you want to solve this integral, right? Plus limit r tends to infinity integral cr e to the power iota z over z squared plus a squared dz. You remember we solved this integral short while. What was the answer of this integral? This answer is 0 because the virtue of the Jordan's lemma. So it means that if you calculate this integral, you can easily calculate this integral then. So let's do it. And if you have any question, please. This is my contour CR. Let's first do this part, left hand side, which is integral on a closed contour. Let me put a sign on the contour which is counterclockwise. E to the power iota z over z squared plus a squared dz. First extract the poles. What is a pole? dz e to the power iota z over z plus iota a, and because we have closed the contour on the positive x-axis, the pole that lies on minus iota a, let's say, that is over here, anywhere, that is not a problem because that lies outside the contour, and we know that if anything, any singularity lies outside the contour by the virtue of Cauchy-Riemann theorem, Cauchy's integral theorem, the answer is always equal to 0. So what you have to do is you have to solve this one now. What is the answer of it? So this is 2 pi iota, right? 2 pi iota times the residue. What is the residue? You have to put z is equal to iota a, not in this, but in every other term. So then you have e to the power minus a over, 2 iota a. So 2 is gone, iota is gone. So this is pi e to the power minus a. Is fine, over, because you have to put z is equal to iota a. Iota squared becomes minus 1. You have to put z is equal to iota a, not over here, iota a, 2 iota a, and then you have e to the power iota z, z goes to iota, so you have minus e to the power minus a. And then, so you have the answer of a left hand side. So pi e to the power minus a over a is equal to integral minus infinity to infinity e to the power iota z over z squared plus a squared dz plus limit r to infinity. Let me write it only once, CR. And by the way, you got the answer, isn't it? This is 0. So It means you have minus infinite to infinite cosine z plus iota sine z over z squared plus a squared dz is equal to pi e to the power minus a over a. Now you compare the real and imaginary parts. And this implies is, let me write over. So you have integral minus infinite to infinite cosine z 1 over z squared plus a squared is, of course, dz, yeah, is equal to pi e to the power minus a over a. And sine of z over z squared plus a squared dz is equal to 0. In any case, you can recognize that this is 0 because this is an odd function. So odd function, sine z is odd function, this is an even function. So ratio of odd and even is an odd function, therefore this is 0. And you can see that this is. So it means that all you have to do is you have to calculate the poles of f of z, put those poles in this exponential, equate the real and imaginary parts, and you can get the integrals of sine z f of z, cosine z f of z. And you just look at the limits from minus infinite to infinite. I think this example is a good point to demonstrate Jordan's lemma. Right? You shrink your contour from minus r to r and then take r goes to infinite. You have to recognize that if you have these kind of integrals, then you can, in any case you have these kind of integrals, I don't remember. You have these kind of integrals in e to the power, exactly, r dot something a, r dot n or r dot a, and when you expand them, you have e to the power iota r cosine theta, something like that. I don't remember. In quantum mechanics, you have these kind of integrals. In, let me think. Definitely in electricity and magnetism for sure, for sure. कह रहे कि इस तरह के integrals ना, for example, if you calculate the electric field from an infinitely long line at a point, then you have cosine components added up, and then you have something x square plus a square downstairs. You can take limit from minus infinite to infinite. Cosine theta you can always write in terms of e to the power iota z plus e to the power minus iota z. These kind of Fourier integrals a lot. Yes, exactly. In the I reserved myself for the propagator, you know. But by the way, this, as sir mentioned, you have these kind of integrals even in the single slit experiment. You know, when the wave goes from the two side, you have sine theta, cosine theta type integrals, and then you can write them over this one. But in that case, you have a real pole, not this one. Yeah. So sir is right. Exactly. You are very right that in the Green's function you have e to the power iota omega over e square minus e naught square. We'll solve this integral definitely in next lecture in quantum mechanical harmonic oscillator case. So the propagator is like this one. Thank you very much, sir. Any other question, please? It's clear? Do you want me to summarize what I have done in this last 1 hour quickly and then move forward? What we have done is first we learned how to solve the double pole. We have given 3 steps for that. We are so obsessed with 3 steps that multiply the order of a pole, take a derivative 1 less than that order, and then put the pole, and then you can get the residue. And then I demonstrated the Jordan's lemma. I said that there are 3 conditions. Again, the pole lies on imaginary axis, and there is a semicircle that you have, and there is a maximum value of that integrand. If you put r to infinite, the modulus of that should go to 0. If these conditions hold, then this integral is 0 on a semicircle of radius r, right? So, and then we have applied that to this one to solve these Fourier integrals. So, any question? Exactly, तभी तो minus r. This has no problem with it. Pole is over here, let's say. यहाँ कहीं भी हो सकता है, no problem. यहाँ तो हमारे पास एक ऊपर एक नीचे. I can also close the contour from this side. then instead of e to the power minus a, I have e to the power a. And you will see that when we do this Green's function, we have to take care of the sign of the exponential term, because we have to see that if these are sine and cosine function, they have to decay exponentially somewhere. So this will definitely help us to choose the right sign of the exponential in the contour integration when we have the propagator. And from that I'll demonstrate how the particle moves in, let's say, one direction and the other particle moves in the other direction in time. So I'll demonstrate this in next lecture. So exactly. So any question? Any further questions? फर्ज कीजिए आपके पास you have sin z cosine z. This is sin 2z by 2. So you have always an option to write these terms. My whole worry is not to calculate this one, but to express in terms of exponentials, e to the power iota z, e to the power minus iota z, etc., etc. Right? So my whole worry was that. And you see, your a is positive, therefore this is exponentially decaying function. Right? You remember at the start we considered a to be greater than 0. This was by chance that you have this integral, you know. Suppose you have something odd function over here, then this perhaps cosine will be 0 definitely, and then sine will not be equal to 0. Then you have to calculate it. But the technique is exactly the same. There is no change in that. But my purpose was to share the technique with you, not to solve any particular integral. What I'm going to do today is I'm not doing the integral, which I'm going now, by using the Cauchy's principal value. I'll reserve this Cauchy's principal value to the 7th lecture, because that full lecture will be on that one. But I'll solve the integral with the knowledge that we have till now. Just if I mention somewhere Cauchy's principal value, just ignore that. So let me solve something as I said, the integral like this one. 0 to infinite sine of x over x dx, and the answer is pi over 2. Remember, you take a modulus, sine mod becomes 1, right? Just look at the behavior of this integral. For small x there is no problem. Why? Because it goes as sine x becomes x over x, which becomes 1. For large x, if we take the modulus of it, sine x mod becomes 1. It goes as 1 over x dx, it has a logarithmic divergence then. But you see, still the answer is finite, it is pi by 2. How to solve these kind of integrals? These are known as Dirichlet's integrals. Let me solve this one. It has a pole on real axis. You can see that if I have, instead of x, I have z, it becomes sine z over z. And the pole is on the real axis. Why not instead of this I solve the integral e to the power z over z? Because it has exactly the same behavior, because it's imaginary part of this one. So when I take the imaginary part in the next lecture, I will talk about the Cauchy's principal value. So that's why today I am going to solve it with the knowledge that we have right now. So remember, you got an idea what I am going to do now is, I am going to solve this, the integrand is f of z is e to the power iota z over z. Entire function, no problem, except a pole at z is equal to 0, which is a simple pole. So it means that I have, if I draw, I have a pole over here. So what I'll do is, I come from this point, take a semicircle, bypass this contour. On the real axis, once again I have r, and then close the contour with like this one. So this is my x. As I told you that I have reserved no x and y as real and imaginary. You see that this is minus r. Let's take is minus rho plus rho, and then this is r. You are going like this, 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 and this. You bypass the pole. Right? And the pole is on real axis. Let's solve this integral. Any suggestion? Let's take this path to be, one path is C1, other is C2. That is, this is C1. Let's take this is as CR because this is a radius R. Then this take that this has a radius rho, and let's take this as C2. By the way, if I change the direction of this one, it becomes minus C2. Right? Because if I define as this and 0, this is pi. So if I'm coming from this to this, angle becomes pi then. Then I have to change the direction of this C2, and I can write minus C2, no problem at all. There is no loss of generality in that. So, now remember, rho is less than x is less than r. You can take it, if you like, you can equal r. For, let's say this is for C1, right? This is x, so x is maximum is r. And then for C2, you can write minus r, this is less than equal to x, is less than equal to minus rho, right? Because this is more negative than this one. But you see, if I go from this direction, then the limits will reverse. And I can coincide the limits of these two. It means I can write them as the same integral then. I guess you got an idea what I want to say. नहीं, नीचे ऊपर जाने की जरूरत नहीं, pole is on real axis. No problem at all. You can just change this like this one. You can change x to minus x, and then this will reverse. Now let's solve this integral. Do you think your path encounters any pole? What is the answer of these kind of integrals then? So if you write integral of C1 e to the power iota z over z dz plus C2 e to the power iota z over z plus C rho by Cauchy's integral theorem. If you do not have any pole in your closed contour, the answer is always equal to 0. But now we actually made this contour like this one. First we go from this to this, then this, then this, and then this one. Or you can go from this, 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 and this. Because these are added, we are adding them, so it doesn't matter which term you can write anywhere. And you can see that this now, C1 e to the power iota z over z dz plus C2 e to the power is equal to minus C rho e to the power iota z over z dz plus not plus but minus CR. As I told you that if I write as minus C2, you remember for a unit circle, let's take Z is equal to, let me write it as, okay, parametric equation is Z is equal to R e to the power iota theta. So if I define theta and 0 on this side, I can write pi on the other side. So I can go from 0 to pi then. So it means that for theta is equal to 0, Z is equal to R this side. For theta is equal to pi on that side, for theta is equal to pi, z is equal to minus r, and corresponding the limit will change. All I have done is, instead of going in this direction, I took it in this direction, increasing theta. So it means I can then write this integral as, let me solve this left hand side, C1 e to the power iota z over z dz plus integral minus e2. Why I have written minus e2? Because I am on the other side. So e to the iota z over z dz. What is the answer of this one? And you know the answer? No. No. Rho to r e to the power iota r over r dr plus or minus rho to r e to the power minus iota r over r dr. Why? Because you know on one you have minus r, on the other you have positive r. So you have to put that over here, parametric equation. Theta is pi. What is this one? What is this, by the way? Two iota rho to r, sorry, sine of r over r. You see, you have a symmetric limits around this pole. That is the whole idea of the Cauchy's principal value, and I'll come to this one. You have a symmetric distribution around this pole point. And by the way, if you calculate the imaginary value of this one, you will get the sign. So left hand side you have done. What about the right hand side now? What about this one? Please. बाकी इंटेग्रल भी तो करने हैं ना अभी. Why? E to the power iota z over z is 1 over z plus, okay. Let's open the series of e to the power iota z. So if you open the series, the first term is 1 over z plus whatever I have over here is starting from z to the power 0 to z to the power positive. So they are the regular part at z is equal to 0. Only the simple pole. As I told you at the start, that pole is simple. Right? So now you tell me how to calculate it for a small circle, 0. आप तो बता दें. Two pi iota, okay. Then. अभी हमने किया नहीं था सॉल्व. किसको? नहीं छोटा सर्कल है. दूसरे के लिए 0 होगा. Exactly. When I take the modulus of, okay, let me do as you said. Okay, just a moment. Very good, very good. If you take e to the power iota z over z modulus, then you have 1 over z modulus, and when you take r to be infinite, this is gone. Right? Because this modulus is 1, so it is 1 over z. So this goes as 1 over r, and for r goes to infinity, this is gone. Absolutely right. You are once again for the Jordan's lemma. Exactly. Perfect. Now you have to solve only one integral. Solve it then. 2 pi iota and then z is equal to 0. So you have 0 पे e to the power iota z over z is equal to, my answer is 2 pi iota, right? Right? Because the residue is 1. So now you have to there is some mistake over here. Then I take, sorry, this is rho. That is a mistake. Oh, this is not 2 pi over 2 because this is a semicircle, not a full contour. It's a semicircle, so I have to divide it by half. Exactly, no, it's fine. It's pi iota. Now you take rho to be 0 because you can shrink this and bring it as closer as possible to the singularity and take r to be infinite. It means your integral becomes pi iota is equal to 0 to infinite sine of r over r dr into 2 iota. So this implies is 0 to infinite sine of r over r dr is perfect. Exactly, that was the goal, to find these integrals. Now you know how to solve the integrals from minus infinity to infinite, that involves exponential. You know how to solve the integral that involves 0 to infinite. And you know that if you have 0 to infinite and your function allows you to write minus infinite to infinite, if it is an even function, then you can always write it as half of minus infinite to infinite. So that's why I said that only these kind of integrals you will encounter in your undergraduate course. So any question? Now you got an idea if the pole is on the real axis, what will happen. You see this exponential function was the same. All you have to do is you have to expand in the neighborhood of that. You have to make a symmetric circle, shrink its radius to be 0, and the other contours you have to take to be infinite, and that's all. नहीं ये सेमी सर्कल सेमी यार पूरा अच्छा कुछ आएंगे जिसमें इंडेंट होंगे वो मैं नहीं कर रहा जिसमें डिस्क हैं जिसमें कोई डिसकंटिन्यूटी है यू कैन मेक इट बट द आइडिया इज एग्जैक्टली द सेम नो प्रॉब्लम एट ऑल 2 by residue is 1 e to the power iota z for z is equal to 0 becomes 1. हाँ नहीं इस तरह भी क्योंकि आप उसी को पूरा भी अगर करते तो तभी आप सिंगुलैरिटी को बाहर निकाल सकते थे. If you remember this, you have so many singularities. We open these contours, we join, then make a bigger contour that will take. तो उसमें से सिंगुलैरिटी बाहर हो जैसा मर्जी हो, आंसर तो 0 ही था. ठीक है. Now I have a toolkit to calculate all sort of integrals. And remember, let me do one thing very quickly because that I'm going to use in my next lecture. Exactly. अब वो तो स्टैंडर्ड है, हमें पता ही है. यू कैन ट्राई इट. नहीं मैंने कहा जिस तरह ये 0 to infinite में oscillating integral था. You remember 1 over z goes like this one, other is going with z like completely oscillating, and the answer is very strange. It is pi by 2. So you see, Gaussian का तो मैं पता है, वो तो या तो exponentially decaying है, तो e to the minus x squared over a squared is perfectly fine. हाँ लाजमी नहीं जिसका अंडर रूट पाई है वो यही हो. You have to do it. You have to do it. मैंने किया नहीं, मैं बता नहीं सकता. You have, because that is e to the power minus x squared is an even integral. Minus infinite to infinite. dx, I know that answer is under root pi. And you see that, you remember if I put x squared is equal to u, I have to write it and then it becomes like hyperbolic functions. Because this iota is sine and cosine and e to the power minus x is not sine and cosine but sine hyperbolic and cosine hyperbolic, you can express that one. So I am talking about these kind of functions which is e to the power iota z, right? But all you have to do is you have to expand and calculate it. मैं कहूँ हो जाएंगे, आप मान लें नहीं, मैंने किया नहीं, आप करके देखें. She said that if can we do this Gaussian integral with all this methodology? Yeah, yes. No, I said that I haven't done it. Yeah, because that's a very well function. Polar coordinates, exactly. There is no singularity. Whenever you have a singularity, you can do it. वो बड़े standard हैं. Okay, so what I'm going to do in the next lecture, let me demonstrate something, and then I'll do it in detail in the next lecture. Remember, this is a series of n is equal to 1 to infinite 1 over n squared. Answer is very strange, pi over 6. This is the Riemann zeta 2. Once you calculate zeta 2 with the complex variable, you can calculate zeta 4, zeta 6, up to so on and so forth. So till now, by the way, this complex variable not only tell you how to solve the integral, it tells you how even you can calculate these kind of summations. And I'll demonstrate that in the next lecture. All we have to do is, this series is very strange, 1 plus 1 over 2 square, plus 1 over 3 square, plus up to so on and so forth. And if you know this series, by the way, you can also calculate minus 1 to the power n minus 1 over n squared. It can be again written in terms of a zeta 2 by adding and subtracting a few terms. And this I'll tell you in the next lecture. But before that, imagine that if we, instead of this one, if we have some kind of an integral where we have 1 over n squared plus a squared, right? And if I take a is equal to 0, I can retrieve 1 over n squared. And n is a number. So it means that we can define a function which has a pole at z is equal to n. So imagine we define a function which is z squared plus a squared with some pole at z is equal to n, so that we can recover the residue which is equal to 1 over n squared plus a squared. And once I calculate the residue, I put a is equal to 0 and I can make a summation and I can retrieve the Riemann zeta function. And that is the most important thing, I'll do this one in the next lecture. But before that, do you remember the functions cotangent and tangent? They were not the entire function, you remember. What about this function, pi cotangent phi z? You encounter this kind of function a lot when you do condensed matter physics. Bosons and condensation, even paramagnetism. Curie law, you will see that we can recover from 1 over 3 kBt from this one. Can you demonstrate the singularities in this kind of a function? What is cos pi z? For any z to be any integer. How to do it? Suppose that is some integer, then how you can do it? Let me do only this thing today, and then tomorrow and on Sunday I'll do that one. So let me do one thing. Cosine n pi, sorry, not n pi, but let me take cosine pi, and let me add a small part in n, and then I'll take n epsilon to be 0. You can always open it, right? Cosine n pi. I haven't took z is equal to n, but a small change in n also. So I have cos n pi, cos pi epsilon plus sin n pi, sin pi epsilon. Now if I take epsilon to be equal to 0, I can have minus 1 to the power n cosine pi epsilon. And if I take epsilon to be equal to 0, it becomes minus 1 to the power n. Similarly, you can write sin pi n plus epsilon. I took a small variation intentionally, and then you can write it as, what is the sign? Sin n pi cosine epsilon plus cosine n pi sin pi epsilon is correct. This is 0, this is minus 1 to the power n. But for small epsilon, this is what? pi epsilon, exactly. So this is for small epsilon, so limit epsilon goes to 0. This is pi epsilon and this is cos epsilon becomes 1. So now if you write this one, pi cotangent pi z, when you take epsilon to be equal to 0, you can write minus 1 to the power n over minus 1 to the power n plus, sorry, so you have pi epsilon, ऊपर pi आएगा ना, this cancels, so this is 1 over epsilon. And you remember I took z is equal to n plus epsilon. So this implies is epsilon is equal to, perfectly fine. You have recovered a pole, you know, pi cotangent pi z. It has a pole at an integer value of n. Integer value of n, exactly. Z is equal to n. So now you see you have a pole at all integer values. If you embed that pole, multiply it with some function, you can take a generating function, calculate the residue. For example, if I have this kind of function, pi cotangent pi z over z squared plus a squared, and I take z to be n from this pole, you have 1 over n squared plus a squared. I do a sum. In that summation, I can recover the zeta function. And this I am going to do tomorrow. Tomorrow means next lecture. But what I have demonstrated in these 5 minutes is that cotangent pi z has a simple pole at all integer values. Z is equal to n, including 0. Yes. But the good sign is the pole is simple pole. If it is of higher order pole, then perhaps we need to worry about that. But for simple poles, we are not worried. We know the residue, everything other than 1 over 1 minus z with this term is a residue for z is equal to n. So I think let me stop at this point, and then we know we are fully ready to calculate this Riemann zeta function. And someone asked, you know how Riemann know these zeta functions. This Raman Hujan has written these series, and you will see that it's very easy way to calculate the series with this one. And this is also done in the textbook of Rayleigh Hobson. Actually, the idea was that one, in principle we have to go to gamma function and other stuff, but in 8 lectures it's very difficult to go. So I'm just trying to calculate all the necessary tools to do the methods of mathematical physics in future, which involve these complex variables definitely. So any questions, please?
Sir, इसको तो ऐसे भी सोच सकते हैं ना कि cos actually cos और sin.
Exactly, वही सोचे.
Cos is 1, जब numerator 1 होगा.
Exactly, you can always this cosine over sine. When sine goes to 0, it becomes infinite. You apply the L'Hopital rule. Yes. Differentiate upstate, differentiate downstairs, and then put that equal to 0. You can get 1 over pi z. And 1 over pi z becomes this one. Pi is cancelled with this one, and it has all the poles at z is equal to 0 and integer values. So how I can demonstrate that z minus n? If n is 0 there, up to so on and so forth, you can demonstrate that. Absolutely. I haven't applied this L'Hopital rule, but I have applied this nice way to write this series. Okay, so thank you. I think we can stop.